We shall begin this module by discussing about intertemporal choices. Intertemporal choice is how people make decisions regarding what to consume and how much to consume in different periods. For a household with a given income, it can either consume today or save today or consume today with interest. This is intertemporal choice decision that a household has to take. Consumers choose optimally how much to consume and save over time given the path of income and the interest rate. These choices are influenced by the relative value people assign to two or more payoffs at different points in time, like the interest rate. Most choices require decision makers to trade off cost and benefits at different points in time. These decisions may be about savings, work efforts, education, nutrition, exercise, healthcare, and so forth. Since early in the 20th century, economists have analyzed intertemporal decisions using a model which assumes that people evaluate the cost and benefits resulting from a decision in much the same way that financial markets evaluate losses and gains, exponentially discounting the value of outcomes according to how delayed they are in time. Discounted utility has been used to describe how people actually make intertemporal choices, and it has been used as a tool for public policy. Policy decisions about how much to spend on research and development, health and education all depends on the discount rate used to analyze the decision. Model of intertemporal choice involving consumption and investment decisions. In the theory of Irving Fisher developed a model of intertemporal choice by the individual economic agents. The major concern in his theory revolved around consumption, investment saving and borrowing and lending without any uncertainty. His theory was later used for the development of the theory of the financial market. Fisher tried to define how the rational forward-looking consumer will not only relate his current consumption to current time period, but also on the future time periods where they try to maximize the lifetime consumption. After studying this module, you shall be able to know the concept of social welfare function, understand intertemporal choice, understand intertemporal choice substitution income effect, derive the Euler's rule. Now, we will discuss the model of intertemporal choice decisions. Irving Fisher developed the theory of intertemporal choice in his book Theory of Interest of 1930. As against to Keynes, who related consumption with the current income, Fisher's model showed how rational forward-looking consumers choose consumption for the present and future to maximize their lifetime utility. The basis of the work is on consumption. The theory is based on some important assumptions such as consumers are forward-looking and chooses the consumption for the present and future to maximize lifetime satisfaction. His consumption is subject to the total resources available for present and future consumption. So basically, in Fisher's theory, he assumes that the individual lives for two time periods, present and future, and how he optimizes his consumption over these two time periods. According to Fisher, an individual's shifting off to current consumption to future depends on four characteristics of his income stream: the size, the time shape, the composition and risk. Besides this, foresight, self-control, habit, expectation of life and bequest motive or concerns for lives of others are the five personal factors that determine a person's impatience, which in turn determines his time preference of consumption. These factors makes him decide whether consumption in future will be more beneficial than today. His two-period optimization problem is given by considering the optimal choice of consumption over time. Suppose that individuals live for two periods, denoted by subscript 1 and 2. Each period individuals earn income Y and choose how much to consume, that is C, or alternatively save by purchasing bonds, that is B, getting a constant interest rate given by R, on the bonds. The budget constraint for the two periods are given as y1 plus b0 into 1 plus r is equals to c1 plus b1 and y2 plus b1 into 1 plus r is equals to c2 plus b2. Now in this, b0 denotes the bonds with the individual at the beginning of the period 1 and b2 denotes the bond at the end of its lifetime. The budget constraints for each period can be rewritten alternatively as intertemporal budget constraint given by y1 plus y2 by 1 plus r plus b0 into 1 plus r is equals to c1 plus c2 by 1 plus r plus b2 by 1 plus r. According to the above equation, the y1 is the current period consumption, y2 by 1 plus r is the future consumption discounted at the rate r per year and b0 into 1 plus r is the value of the bonds with the interest rate today. Hence, the LHS, that is left hand side, shows the current income of the individual, whereas on the right hand side shows the discounted value of the current and future consumption available to the consumer over the two time period, which is equals to the current consumption, discounted value of next period's consumption and the discounted value of the next period's bonds value. Since income is equals to consumption plus savings in both the time periods, it is well represented in the above equation. Also, the above equation states that the present value of lifetime income and initial wealth equals the present value of lifetime spendings. Individuals live for two periods and are assumed to undertake their consumption over these two periods 1 and 2. Therefore, optimal assets in the final period of individual's life will not be positive, that is, B2 is less than equals to 0 as long as consumers are not satiated. On the other hand, individuals are not allowed to leave behind debt, which means B2 is greater than equals to 0. In equilibrium, each generation is therefore born with 0 wealth given by B2 is equals to 0 and the intertemporal budget constraint therefore simplifies to as below. Y1 plus Y2 by 1 plus R is equals to C1 plus C2 by 1 plus R. This intertemporal budget constraint can be shown on the diagram as given. This consumption can be shown as the straight line in the diagram where the slope of the line is minus 1 plus R. The slope tells us how much of the next period's consumption he will have to give up to have one more of the current period's consumption, that is 1 plus R of the next period's consumption. The negative sign shows the substitution between the two period consumption, that is, he can either consume today or save and consume in the next period along with the interest. The line that passes through the endowment point y1, y2 and has slope of minus 1 plus R, consumers can choose any combination of first and second period consumption C1, C2 on this line. The optimal choice depends on preferences over consuming in the first or second period of their life. We assume diminishing marginal utility of consumption, that is, he wants to consume in both the periods, so wants an interior solution. He does not want to consume all today and have nothing in the next time period, nor does he want to consume nothing today and consume only in the next time period. This shows some complementarity between the consumption today and consumption tomorrow, but as the slope is negative, he will be substituting as well. Hence, preferences are shown to be convex to the origin to inculcate this very characteristics of the consumer's consumption behavior between two time periods. Thus, since individuals prefer to smooth consumption between time periods, indifference curves in figures are therefore negatively sloped and convex to the origin. The diagram also showed the three cases where the consumer is a saver today, is a borrower today and an autarkist. A. Saver. This is shown by the indifference curve that is above the red indifference curve. In this, the current consumption is below the current income, hence the individual saves for the next time period, that is C1 is less than equals to Y1, and thus in the next time period due to these savings in period 1, C2 is equals to Y2 plus 1 minus C1 plus R into 1 minus C1. Thus, depending on consumer's preference in this case, he is a saver in period 1 and hence gets to consume more in the next time period. B. Borrower. This is shown by the indifference curve below the red indifference curve. It can be seen that with such preferences, the consumer is consuming more than his current income in period 1. C1 is equals to Y1 plus B. In the next time period, he will have to pay this debt on whole as well as the interest due on it. Thus, in the next time period, the consumer will have lower to consume than his next period income as he has borrowed in period 1. C2 is equals to Y2 minus B into 1 plus R. Thus, the consumer in this case is a borrower in period 1. C. Autarkist. An autarkist is the one who is always at par, who will not shift current income for future consumption, nor will he shift future consumption for current period. Thus, there is no intertemporal savings or borrowings by an autarkist. Indifference curve for an autarkist is shown by the red indifference curve in the diagram. It can be seen in each period, respective is equals to respective consumption. C1 is equals to Y1 and C2 is equals to Y2. Hence, he is neither a saver nor a borrower in any time period. Now, how does the optimal consumption choice respond to the changes in income? It can be seen that individuals want to smooth consumption over time because of diminishing marginal utility of consumption, and they can borrow and lend freely at interest rate R. Consumption each period is therefore a function of the present value of lifetime income. PV bracket Y is equals to Y1 plus Y2 by 1 plus R in equation. An increase in income in one period only, say Y1, leads to less than proportional increases of consumption each period. However, consumption moves proportional to the changes in the present value of income. Moving on to discuss the intertemporal substitution and income effect. In this, we consider the effect of a change in the interest rate on optimal consumption choice in two periods. Substitution effect. When interest rate R rises, that is, to R dash is greater than R, implies an increase of the relative price of current period 1 relative to future period 2. This simply means that the slope of the intertemporal budget constraints tells us the opportunity cost of consuming today. When interest rate goes up, cost of consuming in period 1 goes up. This makes it relatively expensive than the consumption in the next time period. Hence, according to the substitution effect, he will substitute the relatively expensive good for the relatively cheaper good. Thus, when rate of interest goes up, he will consume less today and consume more in the next time period according to the substitution effect. Hence, it makes him substitute away from current consumption towards future consumption. This is intertemporal substitution effect, which leads to a fall in current consumption and increase in future consumption, increase in savings. The diagram depicts the intertemporal substitution effect as follows. In the diagram, initially the interest rate is R, and according to the given consumer preferences, initial optimal is at C1 star, C2 star, with the slope of the budget line given as minus 1 plus R. Now, when the interest rate goes up to R dash, we see that the slope of the intertemporal budget constraint will change. It will now become steeper, showing that when interest rate goes up, current consumption has become more expensive than the next period consumption. To get the exact substitution effect, we pivot the next intertemporal budget constraint at the original optimal, making it steeper at C1 star and C2 star. We see that the individual's preference has moved up to a higher indifference curve where the current consumption has decreased and next period's consumption has increased to C1 dash and C2 dash. Income effect. Income effect means how the consumer will change his consumption depending on the fact that real income has changed. Here we use the definition of normal and inferior good. For a normal good, we have positive income effect, and for an inferior good, we have a negative income effect. We consider consumption in both the periods as normal goods. So, when interest rate rises, consumer's real income rises, Thus, his intertemporal budget constraint will shift out with slope as minus 1 plus r dash. Since both the period consumption is a normal good for him, he will want to increase the consumption in both the time periods. So, from C1 dash, C2 dash, he will increase his consumption of both the periods. Hence, consumption in period 1 as well as in period 2 both rises. Thus, income effect increases the consumption for both the time periods to C1 double star and C2 double star. Thus, we can see the effect of interest rate rising on the current consumption and future consumption. In period 1, substitution effect led to a fall in the consumption of this period, while income effect led to a rise in the consumption in this period. Since both the effect for period 1 move in opposite direction, the result is ambiguous. That is, we cannot say whether in period 1 has consumption finally increased or decreased. But for period 2, the result is an unambiguous rise in the consumption in that period. The substitution effect and the income effect for period 2 has moved D in the same direction, hence effectively leading to a rise in the consumption in the next period. For the aggregate economy, only the intertemporal substitution effect is relevant since there is no net saving or borrowing in equilibrium, as will be explained later. Aggregate consumption demand, denoted by superscript D, depends therefore negatively on the interest rate and positively on the present value of aggregate income, where C1 to the power D is equals to R bracket minus, comma PV bracket Y bracket plus. Let us now understand the intertemporal choice and Euler's equation. The consumer problem can be studied more formally as given. Suppose that individuals have additively separable preferences over first and second period consumption. So, maximize C1 C2 U C1 plus beta U C2, where the period utility is given by U double bracket is strictly concave, U dash is greater than 0 and U double dash is less than 0, and beta is the subjective discount factor measuring the degree of intertemporal weight by the individual. We assume that the individual discounts future utility with 0 less than beta less than 1. The problem of the consumer is to maximize lifetime utility given in above equation, subject to the intertemporal budget constraint as studied earlier. For example, we can use the substitution method and substitute for C2 from budget line to the utility equation, maximize U C1 plus beta U 1 plus R into Y1 minus C1 plus Y2. The necessary first order condition for this problem is also called an intertemporal Euler equation 8. U dash C1 is equals to 1 plus R into beta U dash C2. The Euler's equation determines optimal consumption choice over time. The left hand side of the above equation is the marginal utility of consumption in period 1, which measures how much the individual values 1 unit of consumption. If the individual saves 1 unit, he would receive 1 plus R units of consumption next period, which would increase lifetime utility by the marginal utility of consumption discounted by beta on the right hand side of the above equation. Alternatively, the Euler's equation can be written as beta U dash C2 by U dash C1 is equals to 1 by 1 plus R. In the equation, the marginal rate of substitution between C1 and C2 on the left hand side is equated to the relative price 1 by 1 plus R. In order to further understand intertemporal consumption choice, consider the following example of a power utility function. Consider the below equation. UC is equals to C to the power 1 minus E minus 1 divided by 1 minus theta. In the equation, the parameter theta is greater than 0, controls the curvature of the utility function, and 1 by theta measures the constant intertemporal elasticity of substitution of consumption between time periods. Utility function in above equation is also called isoelastic utility function. The marginal utility of consumption in this case is simply u dash c is equals to c to the power minus theta, and the Euler's equation becomes c2 by c1 to the power theta is equals to beta into 1 plus r. To interpret this condition, rewrite the discount factor as beta is equals to 1 by 1 plus rho, where rho is greater than 0 is the rate of time preference. For small changes in consumption, delta C is equals to C2 minus C1. The left hand side of this expression can be approximated by C2 by C1 to the power theta is equals to change in C by C plus 1 to the power theta, which is equals to and indifferent to 1 plus theta into change in theta by C. For small values of r and rho, the right hand side of this expression is approximately equals to 1 plus r by 1 plus rho, which is equals to and indifferent to 1 plus r minus rho. Combining the two approximations, the Euler's equation, also known as Keynes-Ramsay rule, becomes change in C by C is equals to 1 by theta into r minus rho. The growth rate of consumption, that is change in C by C, is determined by the difference between the interest rate and the rate of time preference, and the strength of the response depends on the intertemporal elasticity of substitution, that is 1 by theta. Hall 1988 tests the empirical relationship between aggregate consumption and interest rates and finds only a weak relationship between these two variables. Let us now summarize what we have discussed in this module. According to the theory of the intertemporal consumption savings decision, Fisher has tried to show how a rational forward-looking consumer will try to optimize his consumption over two time periods. He took consumption in both the periods to be as normal goods, and hence the preferences between these two as convex to origin, thus showing some substitution between consuming today and consuming tomorrow and two also. With the given market interest rate, he defined the intertemporal budget constraint, and hence he defined how the optimal consumption in each time period will be achieved. Some of the reasons for people to save are: first, consumption smoothing. Agents dislike fluctuations in consumption spending. Second, precautionary motives, fear of unemployment, etc. Third, retirement. Fourth, purchase of real estate or durable consumption goods. The development of intertemporal choice has in consequence for many years been interrupted by the principles founded in what we could consider folk logic. These principles have hindered the ability of the theory to evolve between the 50s and the 90s, and to some extent it continues obstructing its further development. And the dynamic consistency requirement has proven particularly hard to withdraw from intertemporal choice, since its normative limitations hide behind a basic intuition identifying inconsistency with the bad. But this intuition is wrong. There is no ultimate reason why someone behaving only sometimes inconsistently is producing harm to himself, for there is no ultimate reason why the planner makes always good plans for the doer. There may indeed be reasons to consider someone who is continuously abandoning his plans is producing himself harm, but the fact that someone's preferences are such that they may result in dynamic inconsistency once does not imply he will be exposed to continuous dynamic inconsistency, as if an iron rod had totally damaged his brain. The identification of dynamic inconsistent preference structures with the bad relies thus on an invariance assumption saying that preferences remain the same across all periods and circumstances, including the situations in which someone perceives he is caught in a money pump. Naturally, any mathematical representation of choice needs to make such simplifications, or the theory would become completely impossible to handle, but the choice of the normative principles that ought to define validity of theoretical models should not drag these simplifications.